Thanks everybody for continuing the journey. Okay, today we're going to go even deeper in the world of pure rings and pure thresholds. So let me just recall something that we did last time. So last time what's Tuesday? I think we proved that F pure implies F injective. Well, in fact, we proved that F split implies F injective, but in our case, that's the same. Okay. Let me also recall this thing and recall for those who don't have fresh definition of a Gorenstein ring. A local ring R and K is Gorenstein if R is Cohen-Macaulay and its top local cohomology is an injective model. You probably have seen different definitions of Gorenstein ring. If you look at Bass paper on ubiquity of Gorenstein rings, there are like 21. There's a ton. This is the one that we're going to take in this course because we have been working with local cohomology. Okay? If you don't remember what's an injective model, so this just means that this functor is exact. Okay? Or if you are very familiar with injective rings, so this has to be isomorphic to the injective hull of the rest of the field. It's good. Okay. So, theorem by Feather. It's a different term. Let RMK, local ring, local Gorenstein ring. Then R is F pure, if and only if R is F injective. So for Gorenstein rings, this is equivalent. F pure versus F injective. And the key point is, I'm not going to give the proof. I may put in the exercise, but probably not. Is that because in this case, in Gorenstein ring, the top local cohomology is injective hull. So F injective means that you have a Frobenius action here that's injective. You have a Frobenius actions in this injective hull. So you took the dual, and because the dual of this, the matrix dual of this is the ring itself, you get some sort of a splitting back. Yes.
The exactness statement, should it be H to the D instead of I?
Oh, of course. Thank you.
The others are also true, right?
For me?
The others are also true.
The others are true because it's zero. Oh, yeah. So, okay. I just should mention that in the same paper, Feather gave an example of something that is not Gorenstein. It's F injective and not F pure. Let me just give you some open problem for today's session. Let R and K be an F injective. No. A local ring. And F inside R be a non-zero divisor. if R over F is F injective, does or is R also F injective? This is like the deformation problem for F injectivity. If you ask the same question for a pure, it's not true, and that's a result of analog sin, right? But for injective, it's not known, and there are a lot of. Kind of funny, but you put here F pure, then it's true that this is F injective. When you put F injective, we don't know. It's a very important problem in this area. Okay. Is there any questions so far? Okay. So let's go back to the pure threshold, and for that I want to focus in the graded case. So for us, K is going to be again undefined as pure. And again, you can think that K is perfect, or K is algebraic closed, and of course, K has to be prime characteristic, because which is what we are doing. So we have finite desserts of only defining prime characteristic. Second, R is finally generated, standard graded K algebra. And we already know this is just a fancy way to say R is a polynomial ring modulo an homogeneous ideal, and every variable has degree 1. And as we have been running, this is the dimension of R. So an exercise also for today's session, show that E, and as a consequence, the splitting prime is R, homogeneous, in this case. Of course, we need to assume that R is a pure for this to be defined now. Or everything is R and R is homogeneous. Okay. Okay, so now let me recall. Okay. So if R is a pure, we define this. Everyone remembers what was ICP? I'm going to write it because I didn't get any immediate yes, so I'm going to write it. Okay, and I have to add in the notation, the settings, that M is maximum homogeneous ideal. Yeah. Okay. I know we proved it we did a bunch of things for this in the local case, no, but homogeneous grade, standard grade is analogous, a lot of this stuff. Okay. Are we good so far? Okay. So now, since MBCP is outside here, no? We have this, pretty much by definition. We also know that MBCP is contained in E, B plus 1. Actually, if we take here any power that is bigger than BCP, we're going to have this one, no? So then, we have that the class of M, let me do the root of R, sub E, this is equal to 0 in this quotient ring, no? Because of this. B plus 1, and M, B, E, different 0 plus 1 equal to 0. B sub E plus 1. This is just rewriting what we have over here, no? But now, because this is homogeneous and this is terminal graded, this corresponds to take R over I sub T sub E and look at every element that has degree at this B sub E, no? And this is the same. That's what the analogous. So this is telling us that this Gaussian ring, which is zero-dimensional, or this finite length or finite k-vector space, the top degree or the degree of the volume it has something that's non-trivial is B sub B. So we can think of B sub B as the top degree of R over I sub B, which is the same as the zero eigenvariant of R sub I. This is like an exercise you want. Okay. Okay, so now more observations. So because R is n-graded, we're going to have that R1 over P to the E is 1 over P to the E n-graded. Makes sense, no? So if you have the degree of R1 over P to the E, is going to be 1 over P to the E degree of R. Now, would you give me, so since R, another one, is isomorphic to R1 over P to the E, as rings, not as a graded rings, just as rings. There is an equivalence of categories between R model to R1 over P to the E models, no? Let me call this equivalence of categories G, no? Because this is isomorphic and the okay. So I'm gonna find given M, we define M1 over P to the E as the image of M in this functor. Which is a fancy way that do the same thing as we did before. And then, but now this has a structure of R1 over P to the E model, because we think that's what the category takes. But because this has a subalgebra here, this doesn't have a structure of R model. So if we have R times, well, R1 over P to the E times B1 over P to the E, this is clear, this should be R, B, 1 over P to the E. But now if we have R times B1 over P to the E, well, this is the same as R P to the E, B 1 over P to the E. No, this is how the structure is working. Or just multiplied by R, no, so it's not. Okay. Exercise. Show that H M I R 1 over P to the E is isomorphic to H M I R 1 over P to the E. the trick is gonna be that this functor is exact because it's an equivalence of categories. Or just changing things. But also, the idea here that one might want to take is m1 over p to the e, no? But if you take m r1 over p to the e, those two have the same radical. And then doing this, for how we define local cohomology, is the same as doing it over R. So a different way to phrase what I'm saying is, this isomorphic, you can see it as an R modulus, or as R1 over 1 over P to the E modulus. It works in both ways. Any questions? Yeah.
Yeah. More than just R. For any, does local cohomology can
Sorry, I can't hear you.
local cohomology can you prove?
Yes.
Yeah.
Maybe. Yeah. I like to write D as the roots. It also can use with a ton of functors. It's not only that. The iterated local cohomology. I think, X, I think? Or no? Well, with other functors. It's the same thing. I think that's X, but I'm not sure. Okay. So in that sense, then, let's place these two observations together. So P to the E is the top degree of this one. So observation. So B, we have that this is the maximum T such that R over E T is different than 0. No? This is the top degree. But now let's try to see this in R1 over P to the E. So I'm going to put here 1 over P to the E. And then here, extended with R 1 over P to the E. We do this. No, sorry. No, not what I want to say. Sorry. So we discuss how R1 over P, R1 over TCP, this one. That's what I wanted to say. Sorry. Let me write it. This is the max P, such that what we have is R1 over ICP, top degree, different than 0. So, in this game, we can see that BCT over P to the E is the top degree, but now here is, this was an N, this is P1, or let me just call it theta, 1 over P to the E N, such that R over ECP, 1 over P to the E, theta is different than 0. And from what we were discussing the other time, this is what is giving us like the free part, no? In a way, of the free part of R1 over P. So this is telling us that B over E, P to the E, is the maximum degree that a free generator, by I mean is one element such that the R module generated by that splits off R1 over P to the E, minimally of R1 over P to the E. Let me be redundant because I want to be clear. So this means it's R1 over P to the E is isomorphic to some sum of I equals to 0 to certain number, the free rank. No, 1. Free rank of R1 over P to the E, R plus something else, no? This is kind of what we did last time. But because we're in a graded case, this has to have certain degrees. what I'm saying is the maximum of these degrees is going to be B sub E over P to the E. That's what we're doing. Is it making sense? Yeah, yeah.
Setting R over P.
P to the E, of course. Thank you. Okay? And what's happening is if you do this and kill this M and kill M times this part, what's going to stay alive is this. Killing this and then M times this is what's happening. There's a K-vector space with generators to this degree. Okay? Okay, so basically give us the maximum degree that the splits off on R1 over P to the E. Okay, so I'm doing all of this, prove the following theorem with Stephanie, myself. This is what we show. So this one, we have that A sub I of R. Remember, Hoxer theorem. Oh, I have to add a few. Suppose that R is a pure. But then, okay, we know for Hoxter-Roberts that this cannot be positive, no? So we got slightly more. This is smaller or equal than the F pure threshold. So a big F pure threshold, a more negative IF invariant, which translates in a smaller regularity, no? Because as a consequence, the regularity of R is smaller or equal than the dimension minus the FPT of R. So bigger F pure threshold, smaller regularity, and smaller regularity is whatever free resolution you take by any presentation of this. It's not going to be, well, it's the jumps, or it's not going to be as complex if you have this pure threshold big. So it's not only a measure of singularity, it's a measure of singularity that gives us control over the free resolutions. I should mention that we haven't defined what is a strongly regular ring. We're going to define that a little bit later, but let me just mention that it's something more difficult to satisfy that purity. Like, it's the closest to being regular from the point of view of tie closure. So there was a conjecture by Hirose, Watanabe, and Yoshida that say that this is true for any strongly regular ring. So what we're going to show is that this is true, but for a much bigger families of rings. Okay, so let's prove that. And once you have been all this word that just translate things to something more down to earth, not well, I guess to me, like this, to understand the B sub E as certain degrees, we define the pure threshold with the B sub E's because there are other definitions. Then this is not going to be so bad, you will see. So first, we have since M to the B sub E and I sub E are homogeneous, we can pick F that is inside MB to the E minus A sub E. This is possible by the definition of B sub E. homogeneous of degree BCP, no? Because we know that every element in BCP, well, we can look at the generators, and every element in BCP plus 1 is going to be 0, no? It's going to be here. So we can pick something homogeneous of this degree, BCP. Okay, now, because this element is not in ECP, there exists a map free 1 over P to the E to R, such that phi of F 1 over P to the E is equal to 1. But because these two are graded, I mean, this is n graded, and this is 1 over P to the E n graded. But because 1 over P to the E times n contains n, we can think these two elements as 1 over P to the E n graded, or just graded by the rational if you just want to make this thing easy. So we can pick these to be homogeneous. And because it tends to 1, it has to be homogeneous of a certain degree. Just to make life easier, this is going to be minus b to the E. Let's make this of degree 0. Okay? So now, I want to look at the map that sends R to R1 over P to the E, that sends 1, or any element R, to R F1 over P to the E. So the image of this map is going to be the R modulo here, generated by F to 1 over P to the E. But again, I want this to be homogeneous of degree 0, so I do this minus BCP. Okay? And we can see that taking bar phi with phi is going to give us the identity in R. Okay? That's pretty much what we did before, but now we're attaching degrees. Okay, so let's take local cohomology. H, I, M, R. And then H, I, M, R, 1 over P to the E. And then from here to here, we have the map induced by phi, so tilde. And then we have back the map induced by bar phi, so let me call that bar phi tilde. And because the composition is identity, when we apply the local cohomology functor to this composition, we have to have the identity. So this means that this is surjective and this is injective, no? Because the composition is isomorphic. Are we good so far? But now this is graded, no? So let me just put here minus b over p to the E. Okay. So if everything here vanishes at some degree, this that is contained because this map is injective has to vanish too. So this is a different way to saying that the top degree of this, which is the A invariant of this, is less or equal than the top degree of this one, which is the A invariant with the respective grading of this one. Are we good so far? Okay, so now what is going to be this? Well, this is just a shifting. So this is the A invariant of R plus B E over P to the E. And then this one, well, remember, this is the same as H I M R 1 over P to the E. So we use this equivalence to see that this is the same as the A invariant of R over P to the E. And notice that this inequality does not relate to either bar phi or phi, no, it doesn't relate to F. We just have an inequality of A invariance with the BCP over there. So what happened when P goes to infinity? Well, nothing happened to this. This is the pure threshold, and this is 0. So, 8I sub R plus the FPT, which is what I wanted to show. And the consequence of the regularity is just by how we define the Castelnau function regularity. Okay, so we have it, and solve the conjecture, that conjecture, by Hirose, Watanabe, and Yoshida. Okay, we're going to see an application of this, but for that, I need to also recall a theorem that we're not going to prove. This is also with Alessandro. So, it's more like a proposition. Is there a question?
So the twist of the ring uses the same twist in the Lagrange model.
Sorry, can you say that again?
And that's the twist. Twisted the
Yeah.
and it's the same twist.
Yes. Because we're changing what is the degree, it doesn't matter. When we get the check complex, everything is like the same degrees. It's very nice. Okay, so notice FPT of R is smaller or equal than the FPT of R modulo every minimal prime of R, and FPT of R is smaller or equal than the FPT of R over the splitting prime. Something that I'm saying here indirectly is that you have a pure ring. So, as you have said, suppose that R is a pure. Then, well, if I'm saying a pure threshold, the ring has to be pure, no? Anyway, so the pure threshold of what we're saying here implicitly, is that if R is a pure and you go modulo every minimal prime, that ring is still a pure. Or if you take R and then you go modulo the splitting prime, that's also still a pure. And actually the theorem, if you're familiar with Carl-Schmitt work of centers of purity, is, or Cartier ideals, the theorem is like the pure threshold of R is less or equal to FPT of R modulo every Cartier ideal or every center of purity, which these are specific examples. Okay, so now let me give you another application of how Frobenius works in combinatorics. So we're going to do an application to binomial edge ideas. So in this case, let n brackets square brackets denotes this set, and G is a simple graph over this one with these vertices. So a simple graph is just like a bunch of points with a bunch of lines connecting them, and there are no loops. Every line is just a line that has no direction, and there is only one line. So if you have a line between two vertices, it's only one line. There is no double lines, the lines have no weights, just simple. Right? So, definition. This is introduced simultaneously by Herzog, Hibby, Herzog, Kale, and Rao, and by Otani. And they prove, they define it this way. So let S be polynomial ring in two sets of variables, xn, yn. So we have two sets of variables, two variables for every vertex. Is vertex? Vertex, no? Vertex, thank you. Okay. So the binomial H ideal of a graph G, which we're going to have, is G sub G is equal to xi yj minus xj yi for every ij that is a vertex, sorry, at H in G. So, example, if we have the path, this path, then if this G, J, we have here G, Gj, this is just x1, y2 minus x2, y1, and then y2, x2, y3, minus x3, y2. If we take the complete graph, Pn, so we're taking absolutely all the ages, so we get all the minors. Now this is like telling us, the ages tell us what minors to take in this kind of matrix. No? So this is the complete graph, so this is just H2 of this matrix. Which has been studied a lot now. And well, you might know how it goes from there. Okay. So I would like to prove that, well, a lot of research has been done since these were introduced is to see what of these are Cauchy-Macaulay. What of these give Cauchy-Macaulay rings? Like the C depends totally depends only on the graph or also the graph and the characteristic. You know, all these things that has been done for monomial HARs, there are analogous questions for binomial HARs. There are several results, there are some classifications. There are things, for instance, in the joint work with Arinda Banerjee, we proved that the depth of the quotient is related to the vertex connectivity of G. But there is a ton of work for regularity and stuff like that. No? What I would like to focus is to characterize when the quotient is a Gorenstein ring. And for that, I'm going to use Frobenius map. So let me just see what kind of singularities this have. So I'm going to write it over there. So we'll need the space to write this theorem. So a theorem by René González and González Martinez, independently done by Mitra Colli and Matteo Barbaro. They prove independently that if R is a polynomial ring, over a field over K. Over K, a field of Planck characteristic is within. And then let I contained in R be homogeneous, ideal, and this be an order, a monomial order, such that the initial ideal of I. You are familiar with Grobner deformations or monomer orders. Grobner theory is a square-free monomial ideal. Then R over I, the inner one is F injective. And this follows a theme of several results. No, I mean, we know that the initial ideal is a deformation of the original, and they share similar properties. No, for instance, they have the same Hilbert function. Therefore, they have the same dimension, and they have the same dimensional multiplicity, Hilbert sum multiplicity. And they have been a lot of recent work that when this is square-free, then they share a lot more properties. They have a lot more properties. Not, for instance, recent work of Alconca and Matteo Barbaro prove that they have same invariance, same extreme Alberti numbers. Therefore, they have the same regularity. Pedro showed a poster on Tuesday in which one of his results is that they share the same connectedness, and then this graph of connectivity, they give connectivity, have the same number of components. And so when we have that this is square-free, it's like a better representation of the original. This information is a better representation of the original. And one would expect, well, let's see what happens in the world of F singularities. So what they prove is you have here square-free, which implies a pure, then gives F injective. Okay? Okay? I'm not going to prove this, but we're going to prove, we're going to use this for the result in a moment. Okay, so let me just give some lemmas or theorems, previous results that we need. So the first one is the pure threshold of R over J chi n. So the total the binomial ideals of the full graph, of the complete graph, or the 2x2 minus of a 2 by n matrix. This one is, any guesses? Yeah, I mean, it's hard to get something this complicated in 30 seconds. It's 2. Yeah, I mean, one may expect that it depends on them, but no, it's good. In fact, I mean, a way to prove this is to compare the pure threshold of this one with the pure threshold of the initial ideal. That's fun. Something that I'm saying here explicitly without proving is that this ring is pure. I mean, we know from the theorem that it has to be F injective, but in this specific case, it's F pure. And let me tell you that in general, this. Oh no, I haven't proved this. Sorry, this is F pure. Something that I didn't prove, and I forgot. Sorry. Theorem. This is if let this be lexicographical order. So you just give me order the variables. The next order, let me just write it x1, xn, and then y1, yn. Then the initial ideal of any binomial ideal is square-free. So we know that the ideals given by binomial ideals are F injective, or give F injective rings. And then let me mention the last ingredient. This is by Tiani and Madani. Is if G is not a path, let G be a connected graph. If G is not a path, then the regularity of R over the Van ideal is less or equal than n minus 2. So if the regularity is bigger or equal than n minus 1, it has to be a path. Which, by the way, one can prove that every binomial ideal associated to a path has to be a complete intersection, as you can see here. Because the initial ideal is a complete intersection. And we know complete intersections are Gorenstein. So our first question is, are there more? And if there are more, which ones? So the theorem by Gonzalez Martinez is the following. Let G be a connected graph. So if the equation of the binomial ideal is Gorenstein, then G has to be a path. So the path is the only Gorenstein. It's not only it's a complete intersection, it's the only complete intersection, but it's also the only Gorenstein ring. And as we know, I mean, there is a vast number of Gorenstein rings that are not complete intersections, but in the world of binomial ideals, that's not the case. Okay, let's prove this. So now, since R over the quotient ring is Gorenstein and F injective, by further result, it has to be F pure, no? We know that's F injective from that theorem over there. We know that it's Gorenstein, by assumption, so it has to be F pure. Okay? So let Q be equal to the binomial ideal of the complete graph. In fact, this is a prime ideal, a very nice prime ideal, by the way. And this one, we have that because it's connected, that Q is a minimal prime of this binomial ideal, JG. Okay? So then, the FPT of R over EG less or equal to the FPT of R over Q, which is equal to 2. Now, by the result with Alessandro, we know that the regularity of J over G, we know that this is bigger or equal that its dimension minus the FPT. No, that's what equal. Sorry. T of R over E. It's the first theorem we proved today. Now, something that I mentioned is if the ring is pure, then this is equal. It's not only this inequality that we prove is an equality because it is Gorenstein. And we needed that because the dimension is going to be n plus 1. This one we know that is at most 2. So this is going to be greater or equal than 2, which is n minus 1. So the result with Alessandro, it was this way, no? So this was not good enough. We needed the equality for Gorenstein. But once we have this, together with the theorem of Kendi-Madani, this one is a path. I mean, it has to be that path for how the dimension is done. Okay? So this application of pure thresholds characteristic P. Now, of course, another of these is implicit that it is for prime characteristic, not the field is prime characteristic. But all this behaves well with the classical technique of reduction to prime characteristic because regularity doesn't change. At the end of the day, this is what we have to prove to get this. You can get this in prime characteristic through a field threshold, but then you forget and you say, oh, we have this for every P. Therefore, we're going to have this in characteristic 0 as well. So the result is in both characteristics. I do not know how to prove it without reducing mod P. I also haven't thought much because to me, this is characteristic P is not something I want to avoid. But yeah. Anyway. Okay. Okay, so now,
Sorry, I have a quick
yes.
question. That theorem up there, that's for the very first one you have, the H. That's true for any graph G?
Yes.
Can you explain a little bit of the proof? Why is that true for any G?
I mean, they compute on a specific Grosvenor basis.
Okay.
And initially, the lengths of that Grosvenor basis are square free. And the way they compute this specific Grosvenor basis is, they build it from the structure of the graph. It's like certain kind of paths and stuff like that. It's a lot of combinatorics that I don't have in my head right now. Sure. But it is just from the combinatorics of the path, they build the specific Grosvenor basis that works.
That's what I was asking, is regardless of anything about the graph?
Yes.
Okay.
Yes, the method, the construction of the Grosvenor basis is regardless of the graph.
Okay.
Now, they did look at when the generators, the binomial generators that we have, they already then are a Grosvenor basis. And for that, it does depend on the structure of the graph. It's what's called a closed graph. And it has to do with interval graphs. But that's for the generators to be a Grosvenor basis, not for the initial data to be square free.
Thank you.
No problem. Okay. So now we're going to go back to singularities. So for this, we're going to be we're going to assume that R and K is local. And the usual things, F finite, characteristic P, this is the dimension. But this time I just want to add validation that R is a pure. Okay? So let me mention a few results to motivate some definition. Some definition we're going to do. So the first theorem is the one I was hesitating yesterday to write. This is Alessandro Stefani, Eloisa Grifo, and myself. And so we have that the depth of the ring is equal to the splitting dimension of the ring plus the depth of R localized at the splitting prime. So this has a corollary that depth R is greater or equal than the splitting dimension, which we know is the dimension of R over the splitting prime, which we know that is bigger or equal than the pure threshold of R over the splitting prime. And by the result that we proved that I mentioned before, this is bigger or equal than the pure threshold of R. So this is to say that depth, if we have big depth with FPT, we have high depth. Okay? Or if we have high splitting dimension, we have high depth. Okay? So, natural question will be, well, we know if this is the biggest, that's the dimension, no? The maximum possible is the dimension. But this result of Takagi Watanabe says that if this is equal to dimension, the ring has to be regular. So asking this equal to be the maximum is probably too much. But asking that this to be the maximum might not be. If the splitting dimension is equal to the dimension, then we know that the ring has to be Cohen-Macaulay. Okay? So, corollary, if the splitting dimension of R is equal to the dimension of the ring, then R is Cohen-Macaulay. The question now is, we get something Cohen-Macaulay that's interesting, or it has to be regular again? So, definition, we say that R is strongly regular if for every C dependent 0, there exists an E inside of N such that Phi N different 0 and Phi R1 P to the E to R such that Phi of C1 over P to the E is equal to 1. So this is equivalent to say that for every C, there exists an E, such that E sub E does not contain it, no? So in other words, for every C different than 0, there exists an E, such that C is outside E sub E.
All P.
No, for one Phi. For one Phi is enough.
Okay.
Yeah, no, we ask for alpha, no, there are going to be some that do not work. So, some exercise that you might see coming right now is that R is strongly regular if and only if R, sorry, if the split prime is equal to 0. And you can see this is happens if and only if the S dimension, the splitting dimension of R, is equal to the maximum. Therefore, every strongly regular range is Cohen-Macaulay. And I mean, I'm not proving that honestly because I'm using this theorem, and this theorem uses a lot of things from splittings and a lot of work that has been done by many people, in particular Coxter and Hunicke, could prove actually, let me just write it. Theorem, the Hobson infinity. They prove that if R is strongly regular, then R is cosmical. Of course, I mean the result is before the ORs, no? So it's a lot of the hard work. Or the hard work. Okay, I'll do the work.
So R will be a domain.
Pardon me?
R will be a domain as well.
Yes, yes. And I was planning to put that in the problem we are mentioning here in the problem set, but example, if R is strongly regular, then R is not only a domain, it's a normal domain. I also must mention that if you go and look in some papers, what's the definition of strongly regular? I'm kind of cheating because what I do is take a C, not in any minimal prime. I want to make my life a bit easier, so I just ask for C different than 0. At the end of the day, because we're in a local ring, they have to be domains, and we don't have to have issues with that. But if I were not restricting myself to local ring, then there may be some irregular rings that are not domains. Like take a field, cross a field. For a regular cross a regular ring, no? But because we're in the local case then. Fine. Okay, here's time. Okay. So, what are the examples? No, that's a fair question. Let me do first a proposition. So, let R be an impure ring. No, S, sorry. Let S be an impure ring. So, if R is contained in R, if this one is a direct summand, then R is pure. So, proof. So what does it mean that this is a direct summand? So I have R, I have S, and then we have a retraction from here to here, beta. This is inclusion. And this beta is such that this map, this composition is identity. So here, beta is a map of R models, no? Because S is an R model, R is an R model, it's a map of R models. This is just a different way of saying that S as an R model is equal to R plus something. No. So, we already have discussed this, no? Like, a ring is a pure if and only if R is a direct summand of R1 over P. Okay? Now, if we take these ones, then this is a direct summand of this one, because this is just the same picture, just taking the roots. So we have the same picture, the identity. And then we have beta, the we call beta 1 over P. And you want the identity 1 over P, the inclusion 1 over P. Okay? And here we have this map as inclusions. How do I build and splitting from this one to this one? Well, I go through the path that I can. I can go here. Now this is a pure, so there exists an splitting. So I go through that path, and then I go through that split. And because this commutes, they going this way and then this way, we're going to get the identity. So this is how we see that it is a pure transcript. Okay? Now, Okay, I wait until everybody finishes writing this because I'm gonna mess up with it a little bit. Coffee. Okay, can I start messing up with this? No? Okay. One more. Okay, take a break. Okay. I'll start raising some words. So here, I'm gonna take a pure, and this is pure. I'm gonna write strongly regular, and then here, strongly regular. Okay, that's the statement. Let's do the proof. So the proof of this is a bit different now because here we want to take a C here and then find a map that we want to pick a C here such that C 1 over P to the E goes back now to 1. So here, let's suppose that you have a C here. I'm going to get rid of the color. This. So let's get a C here. Let's take C inside R. Okay? So here, and C 1 over P to the E, no? And I'm going to map from here to here that sends that to 1. Okay, here I go with the inclusion. Okay? And then I know that there is an E here because this is really regular. And a map here from here to here that is what we call phi that sends this 1 to 1. So through this map goes to 1. And then I take the splitting, goes back to 1. So this is like a high, like a version of the proof that we had before, just adding the C 1 over P to the E. So, corollary, direct summands of the strongly regular, not corollary, a statement of the term. Direct summand of strongly regular rings are strongly regular. Exercise regular implies strongly irregular. If this were not true, this would be a bad name. But it's true. So regular rings are strongly irregular. So as a corollary, we recover a classic theorem of Foster and Roberts. So if R is a direct summand of a polynomial ring, then R is Cohen-Macaulay. And well, they were focusing rings of invariance. No? That's how the statement is done now, but this is. Of course, they proved this theorem before tie closure, strongly irregular, and all these were defined. Actually, the proof is one of the things that inspired Hochster to develop tie closure and all these area of primitive algebra. But okay. So this is. So then this tells us that in characteristic P, rings of invariance of finite groups whose order is not divisible by P are strongly irregular. Because those are direct summands of polynomial rings. Another example of strongly operable rings in characteristic P is theorem or corollary, I guess, for this word of Foster and Hünecke is affine normal toric varieties, affine normal toric varieties, or toric, I will say rings. I'm in the fine case, are strongly regular. Because Hofstede, in one of his first papers, he showed that every affine toric variety is a direct Zeeman of a polynomial ring. And actually, that's how he proved that toric varieties are Cauchy-Macaulay. Normal toric varieties are Cauchy-Macaulay. But they are not only Cauchy-Macaulay, they are also strongly regular. Okay. So let me finish with some comments. Tomorrow we're going to prove that determinantal rings are strongly regular, and then discuss a little bit more of symbolic powers with the strong regularity. But today we're going to finish with some comments of other invariants. One other invariant, the F signature that we mentioned yesterday. So let me define these and then mention the main theorem. So definition. I'm going to write first the definition and then I write who defined it. So the F signature of or local FP ring R is defined by is as of R, and this is the limit to lambda R over I sub E over P to the ET. And if you remember, for instance, if the field is perfect, so the field extent, the degree between K and K1 over P is 1, because they are the same, then this measures the free rank of R1 over P. And this measures from your problem set the rank, not this is the free rank, and it gives the rank of R1 over P. So this is equal to the limit when E goes to infinity of the free rank of R1 over P to the E modulo the rank of R1 over P to the E. So a signature is a percentage of all the elements that you have, that of all those ranks, how many of them are free? It's a measure of how free asymptotically R1 over P to the E is. So one expects that this is a measure of singularities, no? Because free equals regular, 50% free, 50% regular, no? Okay, let me mention attribute dispute. So this was implicit in the work that Smith and Vandenberg did regarding rings of differential operators. There is some of these. They didn't define a signature. They just talk to limits of certain numbers, which is one of them is the signature. The people who coined the term was Hünecke and Luski, and they did. They formally defined that this is the name, and then they did a bunch of properties. However, neither of them proved that this exists, that this limit is actual limit. Okay, some people were working with getting the limits up, and then trying to get properties, no? But it was then when Kevin Tucker showed that this limit exists, no? And so this is the story of the definition. So now let me tell you how these measure singularities with two theorems. One is from Unity Industry. They prove that if the signature is equal to 1, if and only if R is regular. So it is as potentials, 100% free, 100% regular, no? Because, I mean, the problem is that, I mean, we know from Kuhn's theorem and some exercises that if this is equal to this, then the ring has to be regular, no? But what we're saying is this is asymptotically equal to this. And we know a lot of sequence that converge to 1, but it's not all 1, no? So what they prove is, well, this measure is the measure, no? And then the theorem that I did is, well, this is by Averbach, Lütke, that says that the signature is positive. So there is a chunk of free semantics here. If and only if R is strongly irregular. So this strong irregularity, this gives a strong irregularity. We know kind of from the definition that it involves a lot of free semantics. But this is telling us how many of them, no? There are as many free semantics as the order of P to the E. Yeah.
In this direction, you need other condition. Regular imply that thing is all.
No, that's the easy one.
Only in multiplicity.
Yeah, it's because this ipsu E is M bracket P to the E, and it's just counting monomers. This one is the hard one. Okay. I stop here to avoid starting a topic that I just gonna not finish. So we continue tomorrow. Thank you.